So good morning. Good morning to everyone. Okay. So before going to today's class, we'll have a discussion on previous concept. Okay? So in this we have discussed about in D and F block element we have discussed about we have discussed about lanthanides, right? So we have discussed about the lanthanides. Now what do you mean by lanthanides? Anyone? Lanthanides are nothing but these are the element, right? So which belongs to 4F series, Total how many elements should be there? Lanthanides. 14 elements should be there, right? So which comes after the lanthanum. So right. So important point here is they are nothing but 4F series. Which comes after the lanthanum. They are called as lanthanoids. Now total how many? 14 elements will be there. So from which element it will start? It will start from cerium to lutetium. It will start from cerium and ends at lutetium, right? So that's where we have the lanthanoids. Okay. Now we have discussed about general electronic configuration. Can anyone write the general electronic configuration for lanthanoids? Can any one of you? General electronic configuration for lanthanoids?
Example 4F1 to 14,
Okay.
5D 0 to 1, 6 to B.
So we
Six
have
to
to take
six
xenon. Then
4F1 to 14,
4F1 to 14.
5D 0
Yes.
to 1,
So 5D 0 to 1.
6S 2.
Yes, 6S2. So this is the general electronic configuration for 4F series element or lanthanoids. Fine. Now these lanthanides, this can be pronounced like this or NIDS, anything is fine. So it can be represented by the symbol Ln. Okay. So it can be represented by the symbol Ln. What do you mean by Ln? It is a symbol for lanthanoids, group of element. La stands for lanthanum. So Ln stands for group of element, that is lanthanoids. Fine. So that's what we have discussed in the last class. Now we will come to features of lanthanoids. What are those properties? Properties of the lanthanides. Now first we will go with the colors. So first we will go with the colors. Now question can be, why F block elements will form the colored compounds or colored ions? So that will be the question. So when it comes to D block, you people have written it as
Presence of D or
so DD transition, right? So color of D block element is due to the DD transition. But when it comes to F block, it will be due to FF transition. So that's what you can tell. One word answer. Why F block element will form the colored compounds or ions? So that is due to the FF transition. So that's what we can tell. Now one point or one thing we can observe here is, if an element with particular atomic number n, with one particular atomic number, it's a number n here, not energy level, so one particular atomic number, then it will have similar color with respect to 14 minus n containing atomic number containing element. Atomic number containing element. All of you have understood? Any doubts? Say for example, if I take cerium, cerium will be having colorless, or it is colorless in nature. It will be colorless in nature. Now which should be the next element which will be colorless? So which should be that next element which will be colorless? That will be 14 minus n. So this is the first element. Cerium is the first element, that means 13th element. That is 13th element, that is ytterbium. That is nothing but ytterbium, which will be having colorless element, which is also colorless element. Got my point? This is an example. Don't worry. No one is going to ask in detail, but you should know that if any element in a 4F series, if they are having one particular color, here I have taken colorless. So cerium as a first element of 4F series, if it is colorless, then 13th element will have the similar character with respect to the color, and it should be colorless only. That's where we have the ytterbium, which is colorless. That's what 14 minus n talks about. So don't get confused. N, here we are not talking about energy level. So here we are talking about the n means atomic number or position. So first position, 13th position. Why? 14 minus n. So 14 minus 1 is nothing but 13. Right? So that's where we have the atomic number or position, which will be represented by the n. Now why they are going to form colors? Many of the element and compound, it will be colored with respect to F block element. What is the reason? Due to the FF transition. Fine? Similar to that of the DD transition. But please remember, when it comes to lanthanoids, whatever color compound or coloring ions will be there, it will not be as that of in D block. D block will going to produce many varieties of colors. That is not observed in the lanthanoids. All of you have understood? Okay? Now we will come to the next one. That is magnetic property. Next one is magnetic property. Anyway, don't worry. From this part, question will not be there like D block where they will ask you to calculate. Here it will not be there, no need to worry. So when it comes to the magnetic property, lanthanoids will have the higher magnetic property compared to actinoids. Lanthanoids will have the higher magnetic property compared to actinoids. And since F subshell is involved, so here not only spinning, which is going to have the effect on the magnetic property, even orbital movement of these electrons will also have the impact on the magnetic moment. So that's where slightly modified equation. So that's where we have nu is nothing but magnetic moment is equal to G into square root of J into J plus 1 Bohr's magneton. Bose magneton. So that's where we have the equation. Don't worry, they have not asked the question or problem on this. For your competitive exams, I have given the equation, that's all. So this is a constant, proportionality constant, G, okay, which you might have studied in your physics, okay. So where J is total momentum, that is with respect to spin or with respect to orbital moment. That's where we have the J. Whether it is there for you? Okay, it's not the equation, I think it's not that. Anyway, so this is related to total spinning plus orbital moment. All together it is J. Okay, so that's where we have the magnetic property, magnetic momentum equation for the F block elements. All of you have understood? Fine. So why F block element can also show the magnetic property? Once again, due to the presence of unpaired electrons. Once again, due to the presence of unpaired electrons. Please remember, same as that of the D subshell, even F subshell will have the less nuclear force acting on them. Whatever electrons are present in D subshell and F subshell, they will have the less nuclear force acting on them. So due to that, they can have the magnetic property wherever unpaired electrons are there. They can show the magnetic property. All of you have understood? So that's where we have the magnetic property. Shall we move to the next one? Okay. So next one is oxidation states. Next one is oxidation state. Okay. Now, when it comes to lanthanoids, I told Ln can be the representation for the lanthanoids. When we are talking about lanthanides, okay, so that's where when it comes to the oxidation state, common oxidation state will be +3. +3 will be the common oxidation state. Okay, so that's where we have the +3 oxidation state, which will be the common oxidation states for the lanthanides. Okay, now for competitive exam or board exam, you can expect the question, which is the common oxidation states for lanthanides. So that can be written as +3. Now the question here is, why lanthanides are having +3 oxidation state? The reason is very simple. When you write the general electronic configuration, so that's where we have the 4f 1 to 14, 5d 0 to 1 and 6s2. Now, when it comes to +3 oxidation state, this is for lanthanides. When it comes to iron, +3 form. Now the same electronic configuration will become 4f 1 to 14, 5d 0, 6s 0. Got my point? So that's where it will have the +3 oxidation state. So that's where it can show the +3 oxidation state. All of you will agree? That's where it will show the +3 oxidation state. Any doubts? Any doubts from here? So that's where we have the +3. This is the electronic configuration. So this is elemental form. This is the general electronic configuration. Fine. So this is bit important. You have to remember. That's where we have the oxidation state for lanthanides. Any doubts? Okay. Now which is the common oxidation state shown by the lanthanides? that is +3 oxidation state. So which are those electrons which will be knocked out? It will be from outermost S subshell and D subshell electrons. Fine. We will come to next one. But there are some elements which will not follow +3 oxidation state. Which will not follow +3 oxidation state. For example, 63, write the electronic configuration. That is 63 means europium. 63, that is nothing but europium. Okay. So what is the electronic configuration for this 63?
4F7, 5D0, 6S2.
5D0, 6S2. Very good. So this is the electronic configuration for europium. Now if you observe this element, whether it can show +3 or it will prefer to show the +3, whether it will show the +3, no, it will prefer to have the +2. It will prefer to have the +2 because it will attain the stability. It will attain the stability having half-filled F subshell. Having half-filled F subshell. What I mean to tell here is +3. Almost all the element, most of the element will show the +3. But there are some element which will have the +2 oxidation state or +2 ions. They will form the +2 ions. So this is one of the example. Any other example which can be another element which can have this property +2? No need to tell this name. Okay, fine. Just tell the atomic number. Gadolinium. Okay. It should be with atomic number 70. It should be shown by another element which is having atomic number 70. Right? Because 7, add 7 to 63, you are going to get the 70. So ytterbium, right? That is ytterbium. So what is the electronic configuration for ytterbium? What should be the electronic configuration for? It will be 4F14, then 5D0, 6S2, correct? 4F14, 5D0, 6S2. So therefore even ytterbium will prefer to show the +2 because it will attain the stability. It will attain the stability. So that's where we have the xenon 4F14, 5D0, 6S0. Okay? So these will help you out in your competitive exams. Please remember. So these are the concepts which will going to help you out in your competitive exam. That's where we have europium and ytterbium which can have the +2 oxidation state. Now can you tell me any other oxidation state shown by this element? +3 common oxidation state. Now we have some of the element which will show the +2. Any other oxidation state? Okay. Write the electronic configuration with 58. Oh, that is cerium, which is having electronic configuration, atomic number 58. Yesterday we have discussed. And I told to remember the electronic configuration. That is xenon. That is xenon. First 4F2, right? 5D0 and 6S2, right? Now cerium, yes, it can show +3, no doubt. Any other oxidation state which can be shown by cerium?
+2.
Yeah, +2, +3, any other?
+4.
Yes, even it can show the +4, right? So that's where we have the cerium +4. If I want to write, it can become 4F0, 5D0, 6S0 because it will attain the inert gas configuration of xenon. Yes, Purnima, absolutely correct. It can show the +4. So any other element? Any other element which can show this one? I think we can have the tuberculosis. No, just to remember, not tuberculosis. It is TB. Simply I am telling tuberculosis, which can be represented as TB. Okay. So now if I take TB, atomic number, Purnima, it can be 65. It will be 65. Now what will be the electronic configuration? 65. What should be the electronic configuration? It will be 4F9, 5D0, 6S2. 4F9, 5D0, 6S2. So therefore, it can have the +4 because by having the +4 oxidation state or ion, now it will have the electronic configuration which is stable. Which will be stable electronic configuration. Fine. So that's where we have some of the element. So don't worry, but you should remember for board exam you can remember which can be other oxidation state shown by the lanthanides, that is +3 along with the +3 which is the common oxidation state. Other oxidation state will be shown as +2, +4. So these are some other oxidation states shown by the lanthanums. So what I mean to tell here is, with respect to the oxidation state, lanthanides are a bit restricted. They are not like D block element where it will go up to +7. So that's where we have the oxidation state, not like D block element where it will go up to +7 and all. So here it will be +2, then +3, then +4, and +3 is the common oxidation state. For 4F series, I am not talking about actinoids. I am talking about lanthanoids. Any doubt in this? So that's where we have the oxidation states for lanthanoids. Now we will come to some of the chemical reaction. Okay, so chemical property. Not much is that, don't worry. Chemical properties of lanthanoids. So Ln. Now when it comes to chemical properties, first one is reaction with hydrogen. Reaction with hydrogen. So what do you feel? Which product will be formed? Because we are talking about F block element, which can be the a product which can be, which you expect. Metals normally with hydrogen, what they will form? So they are going to form hydrides. Mayank has given the answer. They are going to form hydrides. So naturally, same thing is applicable here also. Now when I am talking about lanthanides, when they react with hydrogen, at the temperature nearly 670 Kelvin, at the temperature of nearly 670 Kelvin, they will form hydrides. Okay, they will form the hydrides, respective lanthanide hydrides. Now same way, if you increase the concentration Ln with hydrogen, if you increase the concentration, even they can form LnH3. LnH3. So by increasing the concentration, first one is student friendly. So second one, so I will make it as 2 cross multiply. So this is where we have the 2 types of hydrides which will be formed from the lanthanides with hydrogen. So they are behaving like a metals. They are behaving like a metals. What is the oxidation state of hydrogen here? What is the oxidation state of hydrogen? It will be -1. So in hydrides, hydrogen will have the oxidation state of -1. So that's where we have the one of the chemical reaction. Now if I increase the temperature, now I am talking about reaction with carbon. Reaction with carbon. So when the lanthanum is treated with carbon, when the lanthanum is treated with the carbon at a pretty high temperature, so approximately 2770 Kelvin, approximately 2770 Kelvin. So that's where it's going to form compound which can be called as lanthanum. Yes, it is. It should be carbides. Lanthanum respective carbides. Okay. So that's where we have respective carbides, where it can be present as Ln plus 3 C2 minus 2. Okay, one extra electron. Okay, so Ln plus 3 C2 minus 2, where carbon will be having, each carbon will have, which is the oxidation state for carbon here?
-2. Oh, each, sorry, -1.
It will be -1. Carbon will have the -1. So that's where carbides, normally it is used as a superconductors and all. Okay. So in those materials it will be used. That's where we have the carbides. Different types of carbides will be formed, and this is one of the carbide which I have written, which will be found whenever carbon is treated with lanthanoids. Okay. So this is another thing, another character for metallic character. Okay, they are going to form the carbides, respective carbides. Now, reaction with halogens. Reaction with halogens. When lanthanides are treated with, halogens, where X can be chlorine or bromine. Okay, normally they are going to use the chlorine. So with halogens, they are going to form, you have to heat it. Now they are going to form respective halides. Respective halides, where X can be chlorine, bromine, or whatever it is. Normally it will be chlorine. So that's where they are going to have the respective halides. Okay, so they are going to form halides. Okay, so now cross multiply 2, 3, 2. That's where we have the reaction. That's where we have the reaction. All of you have understood? Okay. So next one is reaction with. Next one is reaction with, which shows the basic character of these lanthanides, which shows the basic character. Okay, whatever I have written, now I am going to write, it shows the basic character, which is normally a character of the metals, right? So they are good donors of electrons. They will form respective hydroxides. Therefore, they will form basic hydroxides. That's what we are going to discuss. So first one, reaction with water. First one is reaction with water. Now, if you take the lanthanum, if you heat with the water, they are going to form respective hydroxide. Respective hydroxide. Respective hydroxide. Okay? All of you have understood? Manvit, today late. Kirti also. Okay. So that's where we have the hydroxide. Lanthanum with water, it will form the hydroxide. Any other product?
Hydrogen gas.
Yes, very good. That should be liberation of hydrogen gas. Right? Now we have to balance it. So here 3 I will make it because oxygen 3 is there. So here also I should make it as 3. Okay. No, it will not become 3 here. I should increase. If I take it as 6, then I can make it as 2 here. Okay, even 6 is not possible because here only hydrogen will become 6. 6 is also not possible. I'll go with the next number 8.
So it's hydrogen here will become 6, but then it will be 12.
No, that's what we'll go on balancing. If I make it as 8, then 8
So 6 was fine, sir.
6.
Oh. Here 12 hydrogens, there 6.
6. Oh, okay, 6 2 is 12. Okay, now here it will become 2. 2. So, okay, fine, yes. Yeah, so that's where we have the balanced equation. And whatever respective hydroxides are there, they are basic in nature. Okay, so they are basic in nature. Therefore, lanthanides, they will form the basic condition with respect to water. They are going to form the basic condition with respect to water. All of you have understood why they will have the basic condition? That is due to the formation of respective hydroxides. All of you have understood? So next one. Next one is reaction with acid. Next one is reaction with acid. That is H2SO4. Reaction with sulfuric acid. So lanthanides with H2SO4. Not lanthanum, lanthanides. Sorry, lanthanides with H2SO4. Now, what can be the product? It will be a metal. It's going to react with the sulfuric acid.
Hydrogen gas and sulfur.
Oh, sir, what is the electronic configuration of lanthanides? So you are talking about general electronic configuration, right? So lanthanides means general electronic configuration. Just now we have discussed. So that is Xe 4F 1 to 14, 5D 0 to 1, 6S2. This will be the electronic configuration for lanthanides. Okay? This is the electronic configuration for lanthanides. Fine? So very important one here is this number. So it should be 4, 5, 6 only. Then only I are talking about 4F series. Okay? Fine, Manvit? So that's where we have the electronic configuration. Okay? Now, with respect to sulfuric acid, what can be the reaction?
Lanthanide,
Respective
sulfate.
sulfate, that is LnSO4. Now you should tell me the numbers.
And
No, numbers you should tell.
2 and 3.
Okay. So here it will be 2, here it will be 3. Because each sulfate minus 2, lanthanum, common oxidation state or ionic form is plus 3. So therefore 3 2 are 6, 3 2 are 6. Fine. So that's where we have respective sulfate. Any other product? Yes, there will be liberation of hydrogen gas. Fine. So sulfate, it is 3 there. So straight away we will make it as 3. Now hydrogen 3 and lanthanum it should be 2. Okay, fine. So that's where we have the reaction of lanthanides with the sulfuric acid. Lanthanides with the sulfuric acid. All of you have understood? So that's where even it can form the salt with acids. That is the character of the metals. They will form the salt with the acids. Okay? Now, next one is reaction with oxygen. Reaction with oxygen. Okay? Now, if I take lanthanum, when it is heated with oxygen, they will form respective oxide. Can any one of you tell me what should be the formula for oxide? I want, Mayank has given the answer, but some of you should tell me what should be the formula of the oxide which will be formed. Fast. Fast. Formula for the oxide. Which is the common oxidation state? Plus 3, or iron which will be formed will be plus 3 iron. So what should be the formula for the oxide? So oxides are those compounds where oxygen will have the -2 charge. So therefore it should be LnO, that is Ln2O3. Ln2O3. Yes, Purnima, very good. Ln2O3. So fine, that's where we have the oxides. Now I can make it as 2. So here I will make it as 3. So here it will be 4. So that's where we have the reaction with oxygen. Fine, all of you have understood? Any doubt? Now the last one we are going to discuss. All these are similar character to that of the metals, alkali metals and all. Same type of character. Okay? So last one is reaction with ammonia. Okay? So that's where lanthanides, when treated with ammonia, what can happen? I will give a hint by writing one of the product. One of the product will be hydrogen gas. These reactions you people have studied in alkali metals, alkaline earth metals and all. But there is slight variation. There they used to form colored solution. But here colored solution will not be there.
Wait.
They will form the nitrides. They will form the nitrides. Now when I am talking about nitride, what is the oxidation state of nitrogen in nitrides? What is the oxidation state? Okay, when Shashank had given the answer, right? But now here, what is the oxidation state of nitrogen in nitrides? Respective nitrides will be formed. So that means formula will be Ln. In that case, what is the oxidation state? -3. Nitrogen will have the -3 oxidation state. So that's where we have Ln. Okay. So 2 and here 3. So therefore here I should make it as 2. So here it will become. That's where we have the reaction with ammonia. All of you have understood? So these are some of the properties of the lanthanides. Any doubt? These are some of the reactions. Okay, chemical reactions with respect to the lanthanides. Any doubt? Okay. Now we will come to the application. So in the application we have one of the important thing. Okay. So that is related to alloy. I can tell even very important also. That is nothing but mish metal. I am talking about mish metal. Okay. So mish metal, it is a alloy. Mish metal is a alloy which is composed of, many times they have asked, even for competitive exams, 95% lanthanides, 5% iron, 5% iron, then very less, negligible amount, very less of like carbon, nitrogen, aluminium, like this we have the combination, some of the element. Okay, so instead of nitrogen, it should be sulfur. Sulfur can be the better one. Even calcium can be included. Yes, some amount of, very less, negligible amount of sulfur, aluminium, calcium or carbon. It will be added. But major amount is lanthanides and 5% of iron. So these are the composition of mish metal. Then what is the use? It will be used in the preparation of bullets. It will be used in the preparation of bullets, shells, etc. It will be used in the preparation of bullets, shells, and a very bad habit some people will be having, that is smoking. While smoking, what they will use? That lighter. So that ignition part of the lighter will also have the mish metal, because when they collide with each other, they will have the property of forming the spark. So it will be used even in lighters also. It will be used in the lighters also. Okay. So that's where we have the application of the mish metal. Fine. Any doubt? So this is very important. Same way, when it comes to cerium, it is having the property of absorbing the UV and heat. Cerium is having the property of absorbing UV and heat. Now due to that, it will be used in the preparation of Crookes glass. It will be used in the preparation of Crookes glass. So that means these are the glass which will be used for like day and night glass, which will become bit dark and all, where different composition will be there. But the main reason or application of here is to have the protection against the UV light and all, or to protect against the heat. In car windows and all they will put, na. So those type, or in goggles they will put. So that's where we have the application of cerium. Okay, we can tell glare reducing glass. Glare reducing glass, a general term. Okay, so which can be called as Crookes glass. Fine. So that's where we have the some of the application, even in which will be used in the lanthanide. Some of the lanthanide salt, it will be used as a laser, used in the laser. Okay, so used in the laser, lanthanide salts, it will be used in the lasers. Okay, so these are some of the important things which you have to remember about the mish metal. Okay, so any doubts in this? By this we have done with the 4F series completely. By this we are done with the 4F series. So please remember, with respect to your exam point of view, oxidation state, try to remember. So don't worry about the name of the element, but remember which is the common oxidation state and which are other oxidation state which will be shown by the lanthanides. Okay, so common oxidation state is +3, and which are those other oxidation state? Other oxidation state will be +2 and +4. Okay, then remember about the general electronic configuration. Already we have discussed with lanthanide contraction. In the transition element itself, we have discussed the lanthanide contraction. Fine. So these are some of the points with related to 4F series. So we will come to the next one, that is 5F series, which are called as actinoids. Which are called as actinoids, or even you can write it as like this as anything fine. Okay, so actinides or actinoids. Okay, so that's how we can represent it. Now when it comes to this particular series, that is 5F series, why they are called as 5F series? Because there will be entry of electron to 5F subshell. It will be entry into 5F subshell. Which period it belongs to then? It belongs to 7th period. It belongs to 7th period. Remember, n minus 2 related to F, right? So 7 minus 2 is 5. So therefore it is 5F series. Okay. Now, Purnima, what is that? Okay, 7th period. Yes, it should be a 7th period. Good. So that's where we have the actinoids. Now, actinoids will start from thorium. Actinoids will start from thorium, where atomic number is 90, and thorium 2. It will end up at lawrencium. It will end up at lawrencium. Okay. So what should be the atomic number for lawrencium?
103.
It should be 103. Add 13 to 90, because thorium itself is one of the element. So therefore 90 plus 13, it is 103. So now why they are called as actinoids? Because in the periodic table they present after the actinium. They present after the actinium. Therefore they are called as actinoids. Okay, so which belongs to 5F series. All of you have understood? Okay. Now one thing you should remember, that when I am talking about these elements, when I am talking about actinoids, most of them, almost all of them I can tell, they are radioactive in nature. Radioactive in nature, and some of them are synthetic. Some of them are synthetic, but majorly they are radioactive in nature. Therefore, their properties are not much studied. Their properties are not much studied because they are all having short lifespan. Unstable elements. They are all having short lifespan. Therefore, they are radioactive in nature. Now, can any one of you write the electronic configuration for thorium? Electronic configuration for thorium. I will write here 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, 7f, 7p, 7d, 7f. So that's where we are having the off-board diagram. That's where we are having the off-board diagram. So we are going up to 7th period now. So I have written up to 7. Can any one of you, which should be the inert gas we should use? We should take the help of radon. For 5F series, always remember it will be radon. For 4F series, always it will be xenon. Okay? So radon is 86. So 90 minus 86, 90 minus 86, it is 4. Radon belongs to which period?
6th period.
It belongs to 6th period. That means you have done up to 6p. So what is next after 6p? It is 7s, 5f, 6d. Right? So that is 5f, 6d and 7s. How many electrons we have to fill it up? 4 electrons we have to fill it up. Observe it carefully. 6d2, 7s2. Therefore, I asked you people to write the electronic configuration for thorium. Thorium in its ground state does not have any electron in the F subshell. Okay? So normally people will write 5F to 6D0. But here it's not the case. Okay? So although 6D comes after the 5F, but still 5F does not have the electron in the ground state of the thorium. Now the question here is, then why the hell they are included in F block element? That is because in their ground state they don't have the electron in the F subshell. That is one thing. And they are having some of the properties or many of the properties which is shown by the other F block element. Therefore, thorium has been included into F block. Fine. So one of the reasons why this is the case here is the energy difference between 5F and 6D is marginal. Energy difference between 5F and 6D is marginal energy difference is there. And please remember 5F is still more outer side, outer to the 4F and all. So therefore this abnormal electronic configuration we can see in the actinoids compared to lanthanides. Okay? So due to that, in the ground state, you should remember this one. In the ground state, thorium does not have the electron in the 5F subshell. Fine? That's where we have the electronic configuration for thorium. Now can any one of you write the electronic configuration for lawrencium? Okay. So electronic configuration for lawrencium. First, Lawrencium. That is last element, na? Naturally it should be 14. Then 6d1, 7s2. Right? So this should be the electronic configuration for Lawrencium. So last element, 5f14, 6d1, 7s2. Observe here carefully. D subshell 2 electron, 1 electron it is there. But in case of the 4f series, it was only 1 electron which was present at D subshell. But here, thorium, first element itself, it is having 2 electron in its D subshell. Fine? So now, can any one of you write the center element in this? What should be the atomic number? It should be 96. Right? It should be 96. Yes or no? So, 90, 91, 92, 93, 94, 95, 96. Seventh element will be having atomic number 96. That is curium. That is nothing but curium. You can remember it as Chief Minister, CM. Okay? So that's where we have the curium. What will be the electronic configuration? Naturally, it's the middle element. So it should have the half filled. 5f7, 7s2. What about 6d? 0? Definitely.
No. It should be 1.
It will be 6d1. It will be 6d1. So like this, we have some of the electronic configuration. If I take 95, that is americium, Am, americium. Now it will be 0 here. 5f7, 6d0, 7s2. Yes, americium. Okay, Am, americium. So why it is 6d0? To attain the stable electronic configuration. Otherwise it will become 5f6, 6d1. So to have the half filled, so it is going for 5f7, 6d0. Okay. Now therefore what should be the general electronic configuration for actinoids? What should be the general electronic configuration? It will be red on 5f, 6d and 7s. So what about 5f? It will be 1 to 14. What about 6d?
First one.
Okay, 0 to 14. What about 6d?
0 to 2.
It will be 0 to 2. What about 7s? Okay, it will be 2. But when I am talking about these elements, thorium in the ground state they don't have. Therefore, normally they will write. You can write it as 1 to 14 also. No problem. Okay, na? So you can write it as 1 to 14. General electronic configuration. Because in the ground state of thorium, it does not have. So even we can write it as 1 to 14. This is the general electronic configuration for actinoids. Any doubts? Anyway, another 15 minutes session is there. After that, this chapter will be over. So which I am going to have in the next class. And after that, we will solve some of the questions for competitive exams related to this particular chapter. Okay? So any doubts in this? We have to discuss about oxidation state, colors, not much is there. So any doubts in this? So it will be on Saturday, right? Okay, on Saturday we will continue with the class where I will be talking about actinoids. first 10 minutes. Then we'll solve some of the questions. So read and come. While coming to the class on Saturday, prepare for D and F, the whole chapter. Then it will be easy for you to answer the questions. Okay? Thank you. Thank you very much. Take care.